any questions? Okay, so remember, we've been doing control. Are there any questions? So we've been doing feedback control, and this is the feedback loop. And I write this every time on Blackboard, just for reference, because I'm doing everything doing feedback now. And we keep on referring either to the loop or to the result of the loop. So I make sure that that's up there. Now, if you remember, at the end of the last hour, we were doing an example. So what had we done previously? We introduced the PID controller, which I probably should write here also. Very nice. I need that somewhere for reference. So let's just recall the PID controller, where we have GC, which is NV prime tilde over E prime tilde, is KC times 1 plus 1 over SI plus S cavity, where this is proportional, this is the integral, and this is the differential controllers. So that's just up there for reference. So at the end of the hour, and so what did we do in the last class or so? What we did is we introduced the PID controller, and we spoke about how wonderful the PID controller is with all of its attributes. But we said it's only great when we can pick KC, tau I, and tau D well. If we don't pick them well, it can be terrible. But if we do pick them well, it can be great. Maybe not optimal, but for any particular system, there might be some fancy special controller that might do a little better. But as far as robustness and being able to handle model error and how the system might change gradually with time, say due to fouling, this is a great controller, a great control algorithm. So we spent the last class talking about ways of trying to pick KC, tau I, and tau D, and we did them in a fairly mindless way. When I say mindless, we did brute force, lots of calculations, picking the best one. So we had it in a logical way of doing the calculations, but there wasn't any deep insight into what was going on in the controller or the system. So we had the brute force method, and then we had a method that was only slightly better, which was the correlation method. And both of them can give you reasonable values, but we haven't gotten any deep understanding into what's going on. And in particular, what we were left with some questions is, how do we know how to make sure that the system becomes stable, stays stable? Either if it's without control, it's unstable, we want to make it stable with control, or if it's stable with control, we want to make sure we don't screw things up and maybe even make it better. So that's sort of the basic issue, and we noted that the difference between the open loop, when we don't have this, we sort of chop this off, say the open loop is when we just have this. Or if you like, you can think of the open loop as just this, where I have no input from here. So I have no error, so the controller is doing nothing. So I'm just going through here. And in that situation, we would like to be able to, well, in the open loop case, we only have the numerator, say over here. In the open loop case, if this is all that's going on here, we only have the numerator, GD. So the stability is dictated by the denominator of GD. Whereas when we have this closed loop, the stability is dominated by a completely different system where we're looking at this particular ratio and we're looking at the denominator. So it's a completely different stability problem, because remember, the stability is governed by the poles, or that is the roots of the denominator. So it's a different stability problem, so it shouldn't be a surprise that if we start out with a system that has certain stability characteristics without control, when we put control on, it's going to have completely different stability. It can have completely different stability characteristics. And that offers us the opportunity to take a situation that without control may do crazy things, and to try to, with control, make it do not crazy things. So, and that's sort of the notion of control when even in international affairs, if you have a country acting crazy, North Korea, for example, then what the West tries to do is to try to put control on North Korea. When they do set off another nuclear explosion, then we cut aid or something, whatever it is. We're trying to do some sort of feedback control. With politics, it's not always that effective. In chemical reactors, we do a better job. Okay, and that's because we have better manipulated variables in chemical reactors than they do in politics. But this is not a politics class. So, did you have a question? Oh, okay. I thought you were saying I was going too slowly because you're going like this. No one ever complains I go too slowly. They usually complain I go too quickly. Okay, so in order to bring home the point of how control can affect the stability of a system, we started looking at an example, a simple example, and the example was the level control. So we have a system where we have V in, we have a tank, and the tank has a certain height. It can overflow or it can go empty. And we measure the level, and if the tank goes a little too high, we can introduce control and pump more fluid out, or if it goes too low, we can pump less fluid out, etc. So what we first looked at is we just did the balance. The cross-sectional area times the LDT is V in minus V out. Little v again, as usual, is the volume flow rate. We went through the method we always do. We don't skip the detail. We look at what happens at t is equal to 0. We subtract. We take the Laplace transform. And then what we did is we spent the end of the last hour looking at the situation where there was no change in V out, where V out prime was 0. So that's a simple case, and that's because there's no control. So this means no control. If V out prime is 0. That is, when the L changes, I'm not reacting, so there's no control. And we saw that G of S was just 1 over AS, and the roots of the denominator is 0, because it's S minus 0. So that says, remember, that says that the system is marginally stable. What does that mean? It means it could go either way. It could be unstable. And then we looked in particular, of course, so we looked in particular what happens if we change Vn by a step function. If we change Vn by a step function, we saw that L prime of t just increases linearly. We inverted it and it increases linearly. That means it's unstable. It's not exponentially unstable, it's linearly unstable. Remember, we said when the denominator has 0, when the root of the denominator is 0, then things go bad linearly, not exponentially. If the roots of the denominator have a positive real part, then they go bad exponentially. Linearly is bad enough. Overflow is overflow. Or if you like, if V prime is negative, if delta V is negative, then it dries out, the tank dries out because this becomes negative. We also look at what happens in response to a sinusoidal input. If we have a sinusoidal input, so this, so V in prime is B sine omega t, just goes up and down, then we saw that the output also oscillates, but it doesn't go down, it oscillates up, and it oscillates with half the frequency, so twice the period. In particular, it doesn't seem like it goes crazy here, but it does continue to oscillate. But the interesting thing is that the frequency has changed. And it's also going as an S squared, not as a sine squared, not as a sine. Well, let's see what changes when we put control on. Let's look at proportional only control. So let's let V out be equal to Kc times the set point minus LT. So this is proportional only. Proportional only control. So now what I need to do is, so this is V out of t for t greater than 0. For t less than 0, I'm going to assume, so for t less than 0, this is t less than 0. So when I subtract them, I get V out prime is equal to Kc times minus L prime. Because the SP, I haven't changed the set point. So now I can stick that in here. I have AS L prime tilde. And of course I can prime both sides. I can tilde both sides. Is equal to V in prime tilde minus KC L prime tilde plus here. Because it's a minus and minus. Minus, minus gives me a plus. And now I bring this to the other side of the equation. I have L prime tilde times AS minus KC is equal to V in prime tilde. Or G of S, which is the output of prime tilde of V in prime tilde, is equal to 1 over AS minus KC. But that's not a useful form, because in order for the control to be good, then I would want KC to be negative. That is, if L is bigger than SP, so I'm above there, then I want to increase what's going in. So if this thing is negative, then I want this to go up. So that says KC had better be negative. So obviously if KC is not negative, things are going to get worse. I'm going to be increasing the error instead of decreasing the error. So here I typically want KC to be less than 0. So in order to do that, let's just divide top and bottom by minus KC. And then here I have A over minus KC times S. And let me multiply by minus 1. 1 minus this. So I can see that my roots, S, so what's the root of the denominator? Root of denominator is S star is equal to, so I have 1 minus KC over A. Because when S is equal to minus KC over A, then I just get 1 minus 1, 0 in the denominator. Okay, so notice, since KC is less than 0, this looks like it's going to be positive. That's no good. So let's see if I made any mistakes here. Okay, so we can just go directly from here. So if I have AS minus KC is 0, then S is equal to KC over A. Yeah, so I have too many minus signs here. S is plus KC over A. So I have, I screwed something up here. So minus 1 over KC, let's just do it step by step. So this is A over minus KC S. 1 over minus KC. Oh, and this is plus 1. Yeah, because I divided by minus KC. So this tells me that S is equal to KC over A. And since KC is negative, this is less than 0, the system is stable. So as long as KC is negative, that is, as long as when I go above the height, I increase the flow rate out. And when I go below the set point height, I decrease it, then the system is going to be stable. Otherwise, obviously if KC is positive, then S star is going to be positive, and then it's going to be unstable. And since the root is real, it's going to be stable or unstable without oscillation. The height's either going to go up or the height's going to go down, which makes perfect sense when you look physically at what's going on here. So what have we done here? By introducing control, we've taken a system that was unstable and we've made it stable. And in particular, we can invert it if we have L prime of P. We want to come up with that. So first let's do L prime tilde S for a step. So that's equal to 1 over minus KC divided by 1 minus A over KC, 1 plus A over minus KC S, times delta V in over So notice this says just a 1 over s and a 1 plus st in the denominator. This is t. So we can invert this. So I have the constants, delta V in, divided by minus kc. And then that's multiplied by, again, I need my handy sheet. And what line should I be looking at here? Instead of taking pictures, which you can do at the end, you should be paying attention and you should have your sheet out. What line, I ask you to bring the hard copy of this. It's not so heavy. It's lighter than your computer. You know, old technology, paper. What line should I be looking at?
Can we use 4?
I have 1 over s times 1 over 1 plus st. Where is your sheet of paper? This is really not a difficult construction to bring that one piece of paper with you and to have it out at the beginning of the class so we don't waste 10 minutes with you looking for it when I ask you a question. Line 5. So this is multiplied by 1 minus e to the minus t divided by a over minus b. So clearly what we see is we go from a situation where something is linearly unstable, so no controls, yes control. So I was moving along nicely. Actually, mine would just for t less than 0. I was moving along nicely, and then there was a step change. And then this thing grows linearly, whereas this guy doesn't grow linearly. It goes exponentially to a value. Now notice, if beforehand I was at the set point, this doesn't make the offset go to 0. It goes exponentially to a certain value. And let's notice, so it's going exponentially to a new value, and this new value is delta V in divided by minus Kc. And this is an offset. Because presumably for t less than 0, this was 0, and L of 0 was the set point. So this is assuming that for t less than 0, I was at steady state at the set point. So, and that's no shock to us because we know that with proportional only control, I in fact often get an offset that's non-zero. And for first order systems, we know, and this is a first order system because it's a 1 over 1 plus st, we know that those systems are unusually stable. So, as we saw in a previous example, notice that the offset, the size of the offset is delta V in over minus Kc. I can increase Kc, and that decreases the offset. If I increase Kc, it decreases the offset. And it also shortens the time it takes to get there. So if I decrease Kc, a lower value of Kc, for a lower value of Kc, I have a different limit and I get there faster. This is for a lower Kc, higher Kc. So for higher Kc, I get a shorter offset because the coefficient goes down, and I also get there quicker. I reach it faster because this is t. This is the characteristic time constant, and when Kc gets bigger, when I higher absolute value of Kc. When the higher absolute value of Kc, then decreases the time constant. So, are there any questions? All right, so it's nice to get some feedback and some questions so that I know that you're listening and not just sitting there. All right, so what's our goal? Our goal, this is an example. So in this example, we saw that we can crank KC up as high as we want because this is a first order system. And first of all, we make it stable for any value of KC that's negative, and we increase the offset by making KC large, which we can do for first order systems. We can't do that for non-first order systems. There's generally a limit where we're going to have a problem with stability. And we saw that in a previous class. Okay, so what's our goal? Our goal is to design the control system for the system to be stable. So we want to make sure whether or not the uncontrolled system is stable, we want the control system to be stable. And we want to have a logical way of choosing KC, and if we need TI and or TD as well, how to choose them in a way that gives us some understanding of what they're doing, and not just some sort of correlation or large calculation. Not a place to sleep. Okay, so, and of course, we would like to also have a good sense of how the system with dynamics, with the controller, is going to behave dynamically. And we see how it's going to behave dynamically. So that's a tall order. So we're interested in design stability for control. We're interested in some understanding of parameter effect of KC, tau I, tau D. We want to get some physical understanding of what they're doing, more than what we have now, and we want to get a sense of the system's dynamics. So those are our goals, because right now we really only have correlations. And correlations, despite the way they're sold today as deep learning or artificial intelligence, they're not very intelligent. They're correlations. They're useful, but they're correlations. Intelligence is more where you understand what's going on. Maybe we can call that natural intelligence rather than artificial intelligence. So let's just sort of bring home the message of what stability is. If I have a dependent variable, y, and I have some linear equation, this is with respect to t, and I probably show the coefficients here. Yes, A1 plus an y. So here is a general, this is either linear, this is either naturally linear or linearized. Because even though I may have an nth order derivative, each term has only one y in it. And the y is not raised to any power other than 1. So that's why it's linear. And all our systems sort of look like this, with the highest, if we have n CSTRs in series, we would have an nth order equation. And what you find on the right are typically the disturbances and the changes in the set count. Because those are the things that are what we call the forcing functions. They're the things, the forcing functions that we're allowing. So these are the forcing functions. F of t is just a forcing function. Now, from your ordinary differential equations class, this is an ordinary differential equation, you know that y of t is going to have a homogeneous part. Now let's call this L of y. It's a linear operator of y. L is all these derivatives with the coefficients. So y of t is going to be y homogeneous of t plus y particular of t, where L of y homogeneous is 0, and L of y particular gives me f of t. So this, hopefully you had in your ordinary differential equations class. What book did you use in your ordinary differential equations class? Who was the author? What does no mean? No means I didn't have such a class, or it was so long ago that I've formatted the hard drive?
It was before COVID. I don't remember that part.
What's that?
It was before COVID. I don't remember that part.
Oh, it's like the old way of BC and AD. Now it's BC and AC, before COVID and after. Okay. So there's a homogeneous part that solves the equation this thing equals to 0, and then there's a particular part that just gives me f of t. And what you had in your ODE class is that if L of yt is stable and f of t is bounded, then any instability, well, then this part will, then f of t can't cause instability. Now, where did that come from? We also had that in this class. If you remember, we said that when we have a situation, when we have an equation, so for example, we had y prime tilde is equal to g of s times x prime tilde, where this is the forcing function, and this is the dependent variable. We said that any instability to the system doesn't come from x prime tilde, it comes from the roots of g tilde of s, g of s. So if you recall, we're just saying the same thing here. Stability is governed by the poles of g tilde of s, and not by x prime. If you remember, we noted the poles here, and if the poles were real, then we got a sum of exponentials. If the poles were complex, we could also get exponentials times sines and cosines. So we had a sum of all those terms, and they all came from the roots of g, not of x prime. And here I'm just saying the same thing in different notation, because your book says it uses this notation, but it's the same concept. Any instability comes from g tilde, which here is the homogeneous equation. Not from the right side, it comes from the left side. Because if you remember, when we take a Laplace transform of this will give me an s to the n. This will give me an a1, s to the n minus 1, etc. All times y tilde. This will give me that polynomial that goes in the denominator of g. So it's the roots of the polynomial that comes from here, which is in the denominator of g, that determines the stability. So all we're saying here is that the left-hand side of the equation is that L of y homogeneous, and that's the part that determines the stability. And let's recall the various possibilities for stability, many possibilities. So these are all going to be y prime versus t. Let's do a bunch of them. So this is if all the roots have s just simply real and less than 0, then it's just going to go like this. If s is much less than 0, real but much less than 0, s star of roots, then it's going to go down very quickly, even faster than this. If s is a plus bi with a less than 0, then it's going to go down like this. If s is greater than 0, well, then we got a problem, and it just goes up. If s is a plus bi with a greater than 0, then it goes up like this, oscillates and grows. And of course, if s is 0, then, as we saw, it can go up linearly, as we saw earlier. So these are various possibilities. And of course, there's one more, if S is purely imaginary. And it just looks like this. It oscillates, but doesn't grow. So we've seen all these pictures before, and I'm just reminding you before I go on. So let's see if we can work with this a little bit. Okay, so first let's attack stability. And to do it, let's attack stability in terms of an example. And we're going to take one of our canonical examples, the 3 CSTRs in series. Where this is again, I forget which is which. VA, XA, VB, XAB, etc. So that's the usual, that's the example we've been looking at where 1, 2, and 3, V1 and V2 is equal to V3. So that's the example we've been looking at for a while. And and we also have a reaction A goes to B. That happens with the K. So this is the example we've been looking at for a while, many times. And let's assume that SP prime is 0. So to make life easier, let's let SP prime be 0. GV is GS both equal to 1. And I have a D prime that's not equal to 0. So, and since this is a third order system, so CV prime tilde, where CV is of course what's coming out here, CV. If SP prime is 0, then I have GD over all of this. And let's notice, actually before I do that, let's notice that GD is equal to 1 over 1 plus SPQ times some KD. GP is KP over 1 plus SPQ. So we've come up with this in the past. There's a disturbance here to XAB, which goes through all 3 reactors, and the control happens through controlling VA, which also goes through all 3 reactors. So that's why I have 1 plus SPQ in all 3. And we'll recall that T is equal to 1 over T is 1 over tau plus K. So, and this is equal to 1 plus T tau over tau. So I have T is equal to tau over 1 plus K tau. And now I need a controller. So what controller should I pick here? Let's pick, I think I just want a proportional controller. Yeah, let's just pick a proportional controller. And let's pick a controller, GC is KC, proportional. So that's the setup of the problem. And again, you're going to have pictures of all this. Let's now write what CV prime is. CV prime tilde is equal to KD over 1 plus SPQ divided by 1 plus. I've assumed that GS, so SP prime is 0. I've assumed that GS and GP are 0. So I have 1 plus GP GC. GP GC is going to be AP over 1 plus SPQ times GC, which is KC. And to make life up, so let's just multiply numerator and denominator by 1 plus SPQ. So I've got KD over 1 plus SPQ plus AP KC. And just for numerical, and now I want to put some numbers in. So here I have a form, and notice that the stability of the system depends on the roots of this cubic. We have a cubic equation where the constant term of the cubic is not 1, but it's 1 plus kpkc. Okay? So just to actually do some calculations, obviously I'm not doing the calculations, I'm just reporting the results, is let's let kb be equal to 1, and let's let t be equal to, pick some numbers here, the numbers that they use in the textbook. T is 5, and kc goes from 0 to 50. From 0, starts at 0, goes up. I want to choose many different values of kc. And I think I probably want to let kp be equal to 1 here. Or I'll just let, yeah. So, and let's let kp also be equal to 1, just so I can do the calculation here. So in this case, I have cv prime tilde is equal to 1 over 1 plus st cubed plus kc. And here you can see there's only one parameter that's changed. And let me put 5 here, 5s. So there's only one parameter. And what we're going to look at is the stability here, as the stability of the systems at different values of kc. And so what we're going to plot here is the roots versus kc. Right? So, so this is the real axis, and this is the imaginary axis. And we're going to plot the roots in this plane. So, yes? I can't understand a word you're saying. Can I read what? The last line? CV prime, this line? Okay. CV prime tilde is equal to 1 over 1 plus 5s on v cubed plus kc. Okay, so here we're going to plot the roots. So we're going to plot roots of cubic. And since the roots can be complex, I need a whole plane to plot them. So let's start out, what happens when kc is 0? When kc is 0, then I'm just solving 1 plus st cubed, 1 plus 5s cubed when kc is 0. So that just, the roots are when s is equal to minus 1/5. And all three roots are the same. So when kc is 0, s star is minus 1/5, minus 1/5, minus 1/5. Those are all three roots. So if this is minus 1/5, all the roots are here for kc is 0. Now what happens when I make kc a little bigger? When I make kc a little bigger, bigger than 0, then I no longer have a 1 as the constant, it's 1 plus kc. So the roots are not all going to be the same anymore. So what happens? Okay, so as I raise kc, I'm going to get roots that are real. They're all still negative and real, but they're bigger than minus, well, they're, what's that? Well, let me just make sure I get this right. Yeah. So I'm going to get, as I raise kc from 0, I'm going to start to get roots that are not all the same. I have a cubic, so when I get complex roots, I can only have, since the coefficients of the cubic are real, whenever I have complex roots, they have to be complex conjugates. So I can only have them in pairs, because when I multiply them out, I have to get something where I only have real coefficients. So this, for example, is, I'll call it A, and that's where I raise kc to a value slightly greater than 0, and now the roots are all different. So I have a pair of complex conjugates. This is a value a little above and a little bit below the real x, the same amounts. So I have 3 roots. And as I raise Kc, B, B, B. So etc. C. So this is when, so here what I'm doing is I'm just tracing, I'm solving the cubic for increasing values of Kc. And what you can notice is that so far everything is okay because all of the roots have negative real part. Over here, when Kc is 0, I'm in this situation. However, when Kc is greater than 0, since I have complex roots, I move into this situation, which is also okay because magnitude is decreasing. But eventually I get to a point where, and this is equal to Kc is, do I have a value? Kc is 200. When Kc is 200, so I also have a value over here, 200. Kc is 200. So now I have 3 roots. One of them is negative, is slight negative, but 2 of them are purely imaginary. If they're purely imaginary, I'm in this situation. So by increasing Kc, I've gone from a situation where these are all stable to one at 200 where this becomes marginally stable. So this is all stable. But when I get to 200, it's marginally stable. And when I'm greater than 200, this one is greater than 200, say 250. Now I'm unstable. So what you can see here is by tracing the roots of the denominator, which control the stability, as I change Kc, I go from a situation where everything's stable. First I have a situation Kc equals to 0, where not only is it stable, but it's underdamped. A Kc where it's just exponential decay. As I raise Kc, then I go to one where I have a decay. Please don't sleep in class. This is not a place to sleep. You sleep at home. I go from a situation where I have exponential decay to one where I have decay with oscillations, but still decay. And as I continue increasing Kc, I get to the point where I get marginal stability. And even more, I guess, so this can, at 200, things can grow linearly, which is bad enough. But when I go beyond 200, I can get a situation where it grows, let's just call this 250, where it grows exponentially. So here you can see the role that Kc plays by changing the parameter of the controller. I span pretty much the whole range of possible outcomes. And I get a sense of what Kc is doing as it changes the roots. And this method of doing this, the method is called the root locus method. And it's great when I have only one parameter. In this case, that one parameter is Kc. The only parameter I'm varying is Kc. That's when I have proportional only control. If I have proportional integral control, for example, then I have 2 parameters. I've got Kc and tau I. And it becomes a little more complicated. I have to make a graph like this for each value of tau I. And if I have Kc, tau I, and tau d, then it becomes unwieldy. I have to make a million of these curves. So the root locus method is really useful for one parameter systems. It becomes semi-useful for 2 parameters and it becomes useless if I have to vary more than 2 parameters. I just can't represent everything graphically. But for one parameter, it's very nice because I get to see everything. Questions? So in general, there were 4 methods that you attack and basically that have been around for a long time. So the first method is root modes. Second one are what are so-called Baudet plots. And then there are also Nyquist plots. And finally, there's a so-called Routh-Hurwitz criteria. So what we like about this method is it's graphical. Graphical methods appeal to our understanding, to our sense of what's going on. It's much easier to see what's going on in a graph than it is with a bunch of formulas. So we're trying to prefer graphical methods. This is a graphical method. It involves a little calculation, but it's clear, it should be very clear what's going on, what it's doing. The second method is Baudet plots. And that's what we're going to concentrate on now. And then we'll also get the Nyquist plots. We'll touch on that before the end of the semester. But we'll do Baudet plots much more, in much more depth, because we're going to run out of time. And I doubt if we're going to have time to do it with Routh-Hurwitz. We're just going to run out of time. We need another 2 weeks to get to that. But the whole, our goals are to have methods where the calculations are simple, where you can, where they're good for many, many systems, where we get stability information, and where we understand something about the parameters. So we're going to do Baudet plots and Baudet criteria. Are there any questions? Okay. So here's the part where it's really good to be here as opposed to not being here and just watching the video. I'm not happy with, I'm glad you guys came, but I'm not happy with the attendance here. Is there some exam in another course today? Or just people are lazy? 2, 4, 6, 14. Actually, why don't we take attendance today? Since the attendance is so poor, let's take attendance. Who has a piece of paper that we can use? That old technology paper. Please make sure to write your name in the attendance. Okay, so now let's try the following. What we would like to do is to come up with a technique to learn something about stability. And what we're going to do here is we're going to do the Baudet method. And if you remember, earlier in the semester, we made these Baudet plots, which at the time seemed sort of irrelevant. Why are we making these plots? We just did it for fun. We calculated the amplitude ratio in phi, we had the formulas, but then we decided to plot them. And now we're going to see why we decided to plot them. So here I'm just reminding you what they are. But what's the Baudet method? So let's think of the following situation. Let's look at our picture here. And let's break this strand. So let's start out with breaking the strand. I think that I have to run back and forth. So maybe I'm going to copy that plot over here. That way I don't have to run back and forth. So we've got SP prime, GC, GD, GP, GS, GD, hold on, and CD prime. E, and N, and CD. Okay, so I copied the plot. Okay, so step one is we're going to cut this. Cut the system in. So this is broken, so there's no more feedback loop. I cut the feedback loop. Okay, step 2. I'm going to introduce SP prime is M sine omega. So what happens? Well, we know from what we did earlier in the semester that if there's a sinusoidal input and we don't have any control, then we're going to have a sinusoidal output. So CV prime pillar is going to be sinusoidal, and it's going to have an amplitude. The amplitude ratio is going to be the ratio. So m times the amplitude ratio is going to be the magnitude. Well, why do we say that? CV prime also sinusoidal, and omega for CV prime is the same as omega. But we know that there's going to be an amplitude ratio, and there's going to be a phase lag. So I have I have a sine function coming in, and now I have a sine function coming out. And they have the same omega, but they may have different amplitudes and different phi, and there might be a phase lag. Okay, and now I wait for this thing to come to steady state. Great, steady state. This is, I have a sine in, sine out, no problem. Now what I'm going to do is I'm going to repair the cut. I'm going to get rid of this, so restore feedback. And at the same time, take SP prime to a constant. So what happens there? Well, remember, so SP prime is just a constant, just a number. And now I have this coming back. So maybe I should actually do something before that. Maybe I should call this step 4, and I should do something else for step 3. So this is going to be step 4. But step 3, what I'm going to do is I'm going to vary omega. The omega, so before I wait for, I'm going to vary omega until phi is equal to minus pi. Either plus or minus pi. So remember, phi depends on omega. Phi depends on omega, because phi is the arctangent of the imaginary part of g of I omega over the real part of g of I omega. The amplitude ratio, the amplitude ratio is the magnitude of g of I omega. So both amplitude ratio and phi depend on omega. This is important. So I'm going to manipulate omega, move omega around, and try to get phi of omega to be equal to pi or plus or minus pi. Now what does plus or minus pi mean? Plus or minus pi means it's, well, we'll see, but plus or minus pi means, if you remember, e to the I pi is minus 1. Let's just recall, e to the I pi is equal to cosine pi minus I plus I sine pi. The sine of pi is 0, and the cosine of pi is minus 1. So by having phi is equal to pi, or plus or minus pi, plus or minus. Let's say plus or minus. I can have the cosine of pi or cosine minus pi is both equal to minus 1. What does that mean? What that means is, let's just again notice, if the input versus t. Input looks like this. It's a sine function starting at 0. If I have a phase lag of minus pi, then that means that that same thing is exactly out of phase. It's out of phase, meaning that it's like being multiplied by minus 1 times an amplitude ratio. The amplitude may be different, but they're out of phase. Now, why is that interesting? Okay, well, assuming I can do that, now I close the loop, that is, I repair the cut, and I set the set point equal to constant. So now what I have coming in here is I have a constant coming in, and I have this signal coming back in. However, this constant comes in with the plus, and this comes in with the minus. So what that says is the minus flips this, so that what's coming in is exactly in phase with what I had before. They're exactly in phase. So what does that mean? That means, okay, again, I have a constant coming in here, and now I have a sine coming in. I have the sine coming in here, and then it gets pushed through again. It gets flipped, it gets pushed through again. When it gets pushed through again, it gets multiplied by the amplitude ratio. Every time it goes through here, it gets multiplied by the amplitude ratio. Gets flipped upside down, comes back, gets flipped back up, and then it goes through again. When it goes through again, it gets multiplied again by an amplitude ratio, flipped upside down, and then flipped back up here. So what happens is, the nth time through, and what do I want to call this? So it's CV. The nth time through, if whatever it was is the n minus first time through, on the amplitude ratio, magnitude of Cn, of CVn, is whatever it was the n minus first time through times the magnitude of the amplitude ratio. So obviously this is the amplitude ratio to the n times CV prime over the first time through. So what does that tell me? That tells me if the amplitude ratio at the omega that makes phi equal to plus or minus pi. Let's make that a little neater. At omega that makes phi is equal to plus minus pi. If this thing is less than 1, then the magnitude of CV prime eventually goes to 0 because it's a fraction raised to the nth power. Because when I close it, just keeps going round and round and round and round. By the way, and here E prime is 0. On the other hand, if the amplitude ratio is greater than 1, then CV prime tilde goes to infinity, as n goes to infinity. This is stable, and this is unstable. So here, by doing this thought experiment, as Einstein would call the Gedanken experiment, this thought experiment, we see that the stability of the system, yeah, I can get it by solving equations, but here, the stability of the system simply depends on whether the amplitude ratio, when I make the cut, whether the amplitude ratio at the omega that makes phi is equal to plus or minus pi is greater than 1 or less than 1. So that's where these plots really come in. That'd be useful. So again, let's summarize that. The question of stability boils down to the question: is the amplitude ratio at the omega that makes phi equal to plus or minus pi, is it greater or less than 1? And that's a question that's much easier to relate to. I just have to check that. But let's be a little bit more specific. Let's find a bigger piece of chalk. Amplitude ratio of what? Phi of what? Well, notice the amplitude ratio of phi when I made this cut. When I make the cut, I'm looking at the amplitude ratio of GC, GV, GP. And had I made actually times GS. So what is going to get fed back in here? It's going to be, so actually this thing, I could have, should have actually just put it over here. Rather than here, what I care about is what's over here, right before the cut. So, and phi in this thing. And this is called, this transfer function is called the G open loop. It's not really, it's open loop with respect to Baudet. It's not what we call here when I have no control. G of no control is just GB. But G open loop is GC, GB, GP times GS. So it's, you put something in here, and it's, what do you see, what's the G to get up to be where the scissor are, where the scissor is, where the scissor is. Okay, so let's see if we can work with that. That's actually quite cool. So, are there any questions on that? All right, well, let's look at an example. Let's look at the first order system. So here we have a first order system. And here I put it up here to remind you. Remember, first order system G is 1 over 1 plus ST. Or I could have a KP up here, for example. If I have a first order system, then we saw that no matter what I do to phi, omega goes to minus infinity, phi goes to 0. And when omega goes to infinity, phi goes to minus pi over 2. In particular, no matter what I do to omega, I can never get it to go up to pi, and I can never get it to go down to minus pi. So I can never fulfill this condition. So I can never get this resonance condition where a curve will be in phase with itself when it goes around and start adding up. So for a first order system, I can never get phi to be equal to plus or minus pi for any value of omega. If I can't do it, then I can't get resonance. So I never get this adding on top of itself. So therefore the system is stable. The system is stable. And then we knew that. We knew that all first order systems were stable. That I really, no matter what I did, I couldn't get the first order system to go unstable. That's unusual because it's first order. What if I have a second order system? Well, we're going to see this in two different ways. One different way is if you remember in the second order system, here again I have the amplitude ratio and here I have the phase lag. The phi, when omega goes to minus infinity goes to 0, And when omega goes to infinity, we said it goes to minus pi. So I can't get to minus pi until omega goes to infinity. For any finite value of omega, phi never is always bigger than minus pi. So again, the second order system also never get to. They also never get to phi is equal to plus or minus pi. So again, I have stability. Now when I say second order, I am not talking about GP. I'm talking about this product, KC, KV, GC, GV, GP, GS. So even if GV and GS are both 1, if GP is a first order system, and I have integral control, because that's going to give me a power vest in the denominator, this will give me a 1 plus ST, then I'll get something that's stable with the integral control. So that's going to be stable. Now, let's just look at this in a little bit of detail. If you remember, how did we come up with this Bourdais plot? Let's remember that in the Bourdais plot, we needed to know something about the arctangent function. So let's just remind you what the arctangent looks like. So if this is the arctangent of x versus x, so if this is pi over 2, and this is minus pi over 2, and where's my pink chalk? And here I have minus pi, and here I have minus 3 pi over 2. Plus pi, and plus 3 pi over 2. If you recall, the curves look something like this. Now why is that? Because the sine of 0 is 0. So the arctangent, whereas the sine, let's look at the tangent is sine over cosine. So if the cosine, when is the cosine 0? The cosine is 0 at pi over 2 and minus pi over 2, at all pi's over 2. At pi over 2, the sine is 1. So this is plus infinity. So plus infinity, the tangent is infinity. At minus infinity, over here, when the tangent, I'm sorry, minus pi over 2, the tangent is minus infinity. And this repeats. Okay, so let's just notice, we looked at this quantity here. Let's make it big for second order. The arctangent of minus omega t over 1 minus omega squared t squared. Now let's just follow it. Remember, when omega is 0, then I have the arctangent of 0 over 1 is 0. Now, let's see what happens as omega can't be negative. Omega starts at 0 and it goes up. So when omega is a little bigger than 0, so omega t is less than 1. This is negative, and this is less than 1. So I have a negative quantity over negative over positive, it's negative. So if the arctangent of a negative quantity, so I have a negative quantity over here, so the arctangent is going to be something between 0 and minus pi over 2. Pretty much like what I had here. Now what happens when I get to a value of omega, that omega squared t squared equals 1? If omega squared t squared equals 1, and I'm coming from this side, so omega t is positive, minus omega t is negative, and this thing goes to 0. So a negative number over 0 is minus infinity. So that's just saying, great, this is going to minus infinity, so therefore I'm going to pi over 2. So when omega t is equal to 1, then the arctangent gives me minus pi over 2. So this value, when this is over here, minus pi over 2, corresponds to the point where omega t is equal to 1. However, what happens when I go slightly past it? So now I'm a tiny bit bigger than 1. If I'm a tiny bit bigger than 1, then the denominator is negative, and the numerator is also negative. So when, if I go backwards a little bit towards 1, towards omega t is 1, this is negative, but this is going to 0. Negative over negative is positive, and I have a positive thing over 0. So this ratio goes to plus infinity when I approach it from bigger than 1, and it goes to negative infinity when I approach it from less than 1. So this point jumps to here. And that's why when I go past 1, when omega t is greater than 1, I jump from this branch to this branch, and I'm moving along here. And when do I get to minus, and I can actually get to minus pi. But I get to minus pi, when do I get to minus pi? When the cosine gain is 0. I'm sorry, when the sine is 0. I get to minus pi when the sine is 0. So that's what happens when, how do I get, so the arctangent is 0, that happens when omega t goes to infinity. When omega t goes to infinity, the 1 becomes negligible here. The minus omega t cancels at minus omega t, and I just have 1 over omega t. So as omega t goes to infinity, this thing goes to 0, and the arctangent of 0 is 0. The arctangent of 0 is minus pi here. On this branch, it's minus pi. So that's how I go from 0 through pi over 2 all the way to minus pi. But I never get to minus pi until omega goes to infinity. Okay, so that's a detailed explanation of how to draw where this curve came from, of how you actually follow it through here. Are there any questions on that? Questions? Okay, so there's now, but what does that tell me? That tells me that maybe if I go to a third order system, notice that a first order system gets me, allows me to go from 0 to minus pi over 2. A second order system allows me to go from 0 to minus pi. That is, the second order system takes me from, first order system takes me from here to here. The second order system takes me from here to here. The third order system may take me from here to there. How do I know that? Well, I don't have time to do an example, but I can show you why that's the case. Because if I have a third order system, then we have, so a third order system is, we know, let any particular g, say g of I omega, is going to be a magnitude times a magnitude times e to the I phi. That is, remember, for any complex number, we can always write the complex number. Any complex number, real, imaginary, is a point in the complex plane. It's equal to its magnitude times e to the I phi. Well, remember, it's the magnitude cosine plus I times the magnitude sine. So that's, I get this little right triangle. We did that earlier in the semester, and we can always write it as e to the I phi. So the product of g's, of gj, is equal to the product of the magnitudes of g of I omega times e to the I times the sum of the phi j's. So the magnitudes, I just multiply them together. But when I multiply exponentials, I add the exponents. Is that clear? Okay, so what does that tell me? This tells me that the amplitude ratios, of the OL is just equal to the amplitude ratio of C times the amplitude ratio of V times the amplitude ratio of P times the amplitude ratio of S. That is, the amplitude ratio is just multiplied. But phi of the open loop is just equal to phi C, phi V, phi P, phi S plus. The amplitude ratios just add, but the amplitude ratios multiply, the phase lags add. So that tells me why in the first order system I only went to minus pi over 2, and the second order system I went to pi over 2. Because I can think of a second order system as two first order systems in series. Therefore, if they're in series, then I multiply the g's. And if I multiply the g's, that tells me that phi just add. So the phi of a second order system is the sum of two phi's of first order systems. And therefore, the phi for a third order system should be the sum of three phi's for three first order systems. So that's why we expect phi for the third order system to allow me to go from 0 to minus 3 pi over 2. And in the next class, we'll show an example where we do that, where we can actually do the Bouguer's method in great detail for a situation where we'll see instability. Are there any questions? Okay, we had an attendance today that was very poor. We'll get that on there. So I'm reporting, I am taking attendance, and if you missed too many classes, you have the pleasure of taking this class again next year. No, unless someone is sick and doesn't come in because they're sick, they have no excuse for not coming in. Can I get the attendance sheet, please?